There's going to be a lot of interaction today, so I'd like to draw your attention to the answer bar at the top of the screen. It's going to be quite detailed and advanced, I hope. First thing I'm going to do is, first thing we need to talk about is a new type of drawing system, a new way of drawing things. It's called summation blocks or function blocks, and it's a way of drawing out control systems. There's two things that we draw when we do function blocks. One of them is the summation block, and it's a circle, and in the summation block we do addition and subtraction. It's either drawn like this as a circle, or it's drawn like this, a circle with a cross through it, and this is showing one signal coming in which has been subtracted and one signal coming in that's been added. So effectively what this does is you'd have an arrow coming out of there, and you'd have signal A there and signal B there, and what comes out of there is A minus B. So that's the sort of thing you do with a summation block. You do addition and subtraction. Anything else you do via a transfer function. Transfer functions, things come in and things go out, and something gets done to them on the inside. It's a function. When it's going in the forward, that's forward. When it's going forward in time, we normally label them as G's. And when it's going backwards in time, we label them as H's. So that's backwards. So this top one is feeding forward. This is feeding from the left to the right, which we say is the forward direction. And the bottom one is feeding from the right to the left, which we say is the back direction. This might make a bit more sense if I show you an example. Here's an example of function blocks used to explain a flow loop. So we have a simple flow loop here. Firstly, I have my set point, and I have some sort of transfer function which allows me to input my set point. I have a summation block. This is a summation block, and what we do here is we take the set point. Let me just write that in. Set point. And we compare the set point to the feedback, which is of course the process variable. Process variable being fed back. And we create an output just here, which we call the error. The error. Now the error is set point minus process variable. That's what the summation block is doing. It's creating an error which is set point minus the process variable. Then we take that error and we do some sort of control decision with it, and then we transmit a value out to a valve, and the valve alters the flow. We sense the flow and we feed that back to the decision-making process. We've already looked at PID, so if I was to say that this section here, that's effectively the PID block. So that section is PID. That's what the PID block does. It compares the set point to the process variable, which is the feedback, and calculates an error, and then based on that error, it makes a decision to output to a valve. All of this stuff here, that's all going in the forward direction. This signal here is feeding back. So that's feedback because it's, well, feeding back. Okay. So that's a simple control loop drawn using function blocks. Now, it turns out that instrument people are amazingly lazy people. It's probably one of the things that characterizes them. So they don't actually bother drawing all of that stuff. This is what they draw instead. this here, that's the set point. It's coming into the summation block, so we just assume it's the set point. This thing here, that's the feedback. It's obviously feedback because it's going back, so we don't need to label it as feedback. We make assumptions like there must be some way of entering the set point, otherwise what's the point? We also make the assumption that, well, we've got a valve out there that we can alter, otherwise, once again, what's the point? Now, just a quick note on set points. If a set point is enterable, if it's locally enterable by the operator, so the operator can just go in and type in a set point, then we say it's a local set point because it's locally enterable. Okay? So that's how we use function blocks to draw a flow loop. And as you can see, it's obviously a loop because it's a big circle. Now this is what we call cascade control. It's one loop within another loop. What I've got here is I've got two loops. I've got a flow loop here, and I've got a level loop here. And I have one loop nestled inside another loop. The way this works is that the flow loop outputs to the valve. The level loop outputs to the set point of the flow loop. So here's the level loop. It doesn't output directly to the valve, it outputs to the set point of the flow loop. Now, as far as naming goes, the flow loop is not enterable by the operator because the flow loop is being dictated by the level loop. Sorry, so the flow set point is not a local set point. It's a remote set point because it's being dictated by another controller. The level set point, on the other hand, is not being dictated by another controller. So we say the level set point is local and the flow set point is remote. I've done a lot of things very quickly there. Are we ready to move on, or have I got any questions? Okay then, let's hammer this home by going into it in some details. Here is a simple flow loop. At the top over here, I've drawn the flow loop in function blocks. Here, at the bottom, I've drawn a representation of what this flow loop actually is. What I've got is I've got a tank, I've got a valve, I've got some sort of flow meter, I'm measuring the flow, I'm going to a flow indicator controller, and that's controlling to a valve. It's a simple loop. It's a simple feedback loop, and this is a representation of that loop in function. So that's flow control. Now, those of you that have done tuning on flow control, this type of flow control, will know that what characterizes a flow loop, flow, is that it is very fast. Very, very fast acting. It's a very fast acting loop. As soon as you change that valve, the flow changes. To the extent where it's very, very difficult to tune using open loop bumps. So that's a flow loop, a very fast acting loop. Here I've got a simple level loop. Now what I've got here is a level sensor, a level transmitter, now I've got a level indicator controller, and now I've labeled the valve as a level valve because it's used to control level. Here is the function block equivalent of the level loop, and once again you can see it's a loop. The set point is just here, set point. Okay, now this is what cascade control looks like. What I've got here is a loop within a loop. So looking at this again, I've got the inner loop, which is the flow loop, which is this bit, and I've got the outer loop here, which is the level loop, and that's kind of that bit. So with this, what's happening is that the level transmitter, instead of, well, the level transmitter goes to the level indicator controller, but the level indicator controller does not output directly to the valve. The level indicator controller, instead of outputting directly to the valve, outputs to the flow set point. Oh, I forgot to mention, level loops are very slow. So the level controller now outputs to the flow set point. So that's flow set point there. The reason we do this is because the flow loop is very fast. The level loop is very slow. If something comes up, for instance, something changes in the circumstances. If we had just a pure level loop, let's just go back to the level loop. If we have a pure level loop, if someone comes along and say, services the valve, so that the valve starts acting a lot more efficiently. If the level transmitter says, oh yeah, the level's a little bit high, open the valve. So the level transmitter says the level's a little bit high, open the valve, and the valve, say, opens from 30% to 33%. Then what will happen is, because the valve is acting more efficiently now, then what we're going to do is, we'll overshoot. Oh, sorry, level's a little bit low. Level's a little bit low, so open the valve. So the level's a little bit low. What's going to happen is we're going to overshoot, because it takes time for the change to occur. And with a level transmitter, with a level tank, sorry, a tank level control, it can take several minutes for the reaction to occur, because level control is a slow control. So we're going to overshoot, and it will take some time before it comes in. So with a small tank, say 100 litres, that could be 15 minutes there. So we could get 15 minutes of bad control. Yeah, go ahead, Jeffrey.
Question. Would the same sort of a principle of control apply if you're using something like sand or concrete, a thicker sort of substance?
Yeah, really. We're going to cover that towards the end when I start talking about capacitance and resistance and how things with how the capacitance affects control. So if you can wait until near the end where we're talking about capacitances, I'll explain it all then. Basically, something that has a capacity like a tank tends to have slower control. Now, with cascade, the tank level is slow, but the level control is slow, but the flow control is fast. Now, if somebody were to come along and service the valve so the valve works more efficiently, if the level goes low, instead of outputting to the valve, the level says, okay, increase the flow by, say, 20 litres. So the flow set point gets increased from, say, 30 litres per minute to 35 litres per minute. Now, as soon as that flow control gets that output, gets that request, it controls, and within seconds, the flow increases. But because the valve's just been serviced, the flow overshoots just a little bit, and it overshoots to, say, 37 litres a minute. Now, the flow control sees that and corrects it. And because the flow control is such a fast control, it corrects that overshoot within just a few seconds, so that the response for the level, instead of it being a long drawn-out oscillation, is a pretty quick response back to the set point. So by embedding a fast loop within a slow loop, fast loop within a slow loop, we effectively get the characteristics of the fast loop on the slow loop. So it's a much better control system now. It will, when things change, and things do change, everything changes, nothing stays the same. Valves are always being serviced, temperatures in outside air temperatures constantly changing. When things change, cascade control responds much better because we get the characteristics of the fast loop being put onto the slower loop. When we're tuning cascade control, we start in and we work out. So you tune the inner loop first, just like you would a normal loop. So you put the loop on local, and you would probably then put it into manual, do an open loop tuning exercise on it, and then once you've got some good values, you bung it into auto, and that's all good. That inner loop is done now. Then you put that loop on remote, and you go to the next outer loop, and then you tune that one, doing open loop tuning, and you tune each loop as you would normally. You completely forget the fact that it's not actually controlling a valve, it's actually controlling the set point of something else. You forget that, you just tune it as per normal. You do the open loop bump, you calculate your time delay, your time constant, your open loop gain, put those values into the equations, get the P and I values, put those in, so it's all the same. When you're doing this tuning, you must ensure that the inner loop is always running faster than the outer loop. So that, just pop back to here for a second, so that here the inner loop must be a fast loop, and it must be running fast. The outer loop must be slower, and it must be running slower. We achieve this by changing the sample rates or the update rates in the PID, so that the inner loop has got a much faster update rate than the outer loop. If you don't do this, then the inner loop will be forever chasing its own tail, as the outer loop doesn't give it a chance to actually control something before it issues a new set point. Now, conventional naming of names for these loops. Quite often we call the inner loop by what it does. It's the flow loop, or the level loop, or the temperature loop, or whatever. And then the next outer loop out, we would call it the cascade loop. Another term we often use is we call the inner loop the DDC loop. DDC stands for Direct Digital Control. So we'd say we have a flow DDC loop, which will be the inner loop, and then we'd have a level supervisory loop. Some of the books use the term master-slave. As far as I know, it's only the books that use this term, because I've never heard it used in industry.